Okay, intro to bonding. First of all, a chemical bond, okay, is a mutual electrical attraction between the nuclei and the valence electrons of different atoms that bind them together, okay? A chemical bond forms for these reasons. Actually, several reasons, but these are the two most important: to decrease potential energy and to increase their stability. Nature always likes things in the lowest possible potential energy that it can get, and it is more stable and lower potential energy to bond things than to them be separate. Okay? Got it? Okay? There are three types. You're going to have to just watch the video. You're not going to be able to do the quiz and this. Okay? There are three types of bonds that we're going to be looking at and that you will be responsible for on the bonding quiz. They are ionic bonding, which happens between a metal and a nonmetal. Okay? Covalent bonding, which is between two nonmetals, and then metallic bonds, which is between metals. Okay? Those are the three types of bonds that we're going to look at. We're mostly going to be looking at ionic and covalent because they do more in our reactions. The metallic bonds just kind of, we don't really do a lot with them. Okay? But you do have to know about them. So ionic bonding, it is the chemical bonding that's the attraction between the cations and the anions. And we said the cations are positive. They're positive. Okay? The cations are positive. That's because if they're positive, did they lose or gain electrons? They lost electrons. Okay? So they lost electrons. If they're anions, then they gained electrons. Okay? The electronegativity difference is greater than 1.7. The electrons are transferred. They're giving and taking. Okay? The cations give their electrons to the anions. So they're transferred. Okay? When we look at a compound, we can tell if it's ionic by the fact that it's a metal and a nonmetal. And the metal will always be listed first. So some examples of those would be NaCl, potassium bromide. Those are two examples of metal and a nonmetal. Okay, can you see where I'm sitting? Okay, sorry. Okay. When we have a covalent bond, we are sharing. Okay, we are sharing electrons between two atoms. We recognize this by the fact that it's between two nonmetals. So examples of covalent could be water, CO2, or hydrogen, which is a diatomic molecule. So those are some examples of covalent between two nonmetals. Okay? We good so far? Hey, will you turn that fan off? Because I'm afraid it's going to show up. Yeah, will you turn that fan off? I'm afraid the noise is going to show up on this. This thing's sensitive. Thank you. So covalent bonding, when they are sharing the electrons, this is just a picture so you can kind of visualize. They're actually overlapping their orbitals and sharing the electrons. Okay, they're actually overlapping. Whereas in ionic, one electron is taken away and given to the other one, and there's a complete transfer. But in this case, they like overlap and share. So they're actually physically bonded together. Okay, when they are bonded together, we call it a molecule, which we'll get to in a moment. There are two types of covalent bonds. And if we're sharing, it's based on whether the sharing is equal or the sharing is unequal. Okay? If the sharing is unequal, so unequal sharing, write that up there, then you get a polar covalent bond. Okay? In other words, one of the electrons is spending more time with one of the atoms than the other one. And that's where the electronegativity comes in. So the electronegativity, whichever has the higher electronegativity, gets to have the electron more, okay? Because it has a greater pull on that electron. So that uneven distribution creates something that we call dipoles. So basically, this side of the molecule is slightly negative because it gets the electron more, and this side is slightly positive because it gets it less. It's not a full-out charge like in anions and cations, so that's why we say it's slightly positive or slightly negative. There are two ways we can show this. This little vector arrow right here is called the dipole, or the dipole moment. Or we can do these little funny, that's a lowercase sigma, no, lowercase delta, which is slightly positive, slightly negative. But whatever has a higher electronegativity, that's going to be the negative side, because it gets the electron more often. If we share equally, in other words, same amount of time they get the electron, then that's called a nonpolar, because they don't create those dipoles. And those have to be less than 0.3, their electronegativity difference. So our diatomic elements, or if it's bonded to the same thing, so if a hydrogen's bonded to a hydrogen, what's its electronegativity difference going to be? 0, because they have the same electronegativity value, so it'd be 0. Okay? So this is just kind of a visual, so you can kind of picture what those would look like, those three different things. Okay? The the electronegativity difference is literally subtracting their electronegativity values. Higher one first, and then get the difference. So if it's nonpolar, you can see that their electron distribution is equal. Okay, even Steven all the way around. For polar, it's like slightly more for chlorine than hydrogen. And then if it's ionic, it's a complete transfer. So it's two separate entities. Okay? Are we good so far? Any questions? Okay. So this is our trend. So we would subtract. Okay? So if I wanted to do, say, HF, I would take the 4 minus 2.1 for hydrogen, and I would get what? 1.9? So that would be its electronegativity difference. Okay? That's how we do that. Covalent bonds. Okay, a molecule is what we call a covalent bond. Okay? So we sometimes refer to them as molecular compounds because they form molecules. Okay? And they are held together by those covalent bonds. The molecular compound is the whole chemical. Okay? And then the chemical formula is your atoms and symbols that tell you how many you have. So like if I had sugar or glucose is C, whoops, I forgot to say I was going to write, sorry. C6H12O6. That means I have 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms in that compound, in that molecule. Okay? So that's, and the chemical formulas are also the same for ionic. Okay? If I said I had potassium oxide, it'd be K2O, so I'd have 2 potassium, 1 oxygen. Okay? The diatomic molecules, have we talked about those in here? Brinkelhoff? Okay. In that space, I want you to write this Brinkelhoff. These are atoms that exist in nature bonded to another atom of the same thing. So in nature, we don't just have an oxygen atom, it's an O2. It's 2 atoms stuck together to make a molecule. Just put it back there. Thank you, Riley. Same thing with chlorine. So the Brinkelhoff is just a way to help you remember which ones are your diatomic molecules. And that's going to be important as we go through the year, especially as we get to reactions. Okay? Does everybody have that written in the spot for Brinkelhoff? I mean, you can come up with your own way to remember it. That's just the way we've remembered it for a long time to help you remember. So if I say it's a Brinkelhoff, that means it's a diatomic molecule. Okay? It's not a name, it's the symbols.
I know it is, but like, it's like a weird word to have to say. Is there any other way to...
You can arrange them however you want. There's all kinds of ways. That's just been a way that a lot of chemists for years have done. Because it kind of sounds like a name. So the formation of a chemical bond, okay, it's the nuclei and the valence electrons, okay? And again, this is the second time that I've said it, so it must be important. The potential energy is lowered. Okay? Yes?
This is covalent, so is it supposed to say chemical?
Formation of a covalent bond.
The last part.
It could be actually both. Yeah. All bonds, they do so to decrease their potential energy and increase their stability. Okay? got that? Okay. The bond length, which is on the next page, is the distance between two bonded atoms at their minimum potential energy. And then your bond energy is the energy required to break that chemical bond and form isolated atoms. So bond energy is how much energy would it be to break the bond. Okay? So when we're doing the bonding, there's something called the octet rule. Do you remember what an octet was? 8. And the outermost what? Which orbitals? Do you remember? S and P. S and P. And the octet rule states this. Maybe it does. Wait, my thing's stuck, but y'all's is not. Okay. Oh my gosh, my thing is acting crazy. So chemical compounds form so that each atom, by either gaining, losing, or sharing electrons, has 8 in its outer energy level, which is the S and P. There are some exceptions. Okay, boron is an exception. It will only get 6 because it only has 3 that it can share. And then, of course, hydrogen and helium only have 2. Okay, don't tell me that helium can form 8 bonds because you have to hit yourself if you do. Okay? So this next part, where it says, in your notes where it says electron dot notation, right after Thanksgiving. We'll do that after Thanksgiving. The next page where it says bond lengths and bond versus bond energy, also after Thanksgiving. And then that brings us to ionic bonding and ionic compounds. So we're going to do this now. So ionic compounds are composed of positive and negative ions that are combined so that the numbers of the charges are equal. So your positives and your negatives have to cancel each other out. And what are the positive ions called? Okay. All right. Most of these are crystalline solids. And it says always, but that's not true. Say most always. Add that most in there. They are most always between a metal and a nonmetal. Most always. In chemistry, there's always an exception, right? Very rarely will I say always, because there's usually some sort of exception. The structure that you're looking at there is lithium chloride. And if you see and you look at it, they alternate between positive and negatives. You'll never have 2 positives next to each other. You'll never have 2 negatives next to each other. It's an alternating arrangement. Positive, negative, positive, negative. Okay? We call ionic compounds formula units. They are not molecules. They are formula units. Because they are not physically connected like the covalent where they overlap orbitals, they're attracted like a magnet is a positive to a negative end, kind of like that. Okay, don't say it's a magnet because it's not. I'm just giving you an illustration. So you got positive, negative, and they're being held together by that electrostatic. So they're not actually a molecule stuck together. So we call them a formula unit. Okay. Characteristics of the ionic bond. Again, nature likes things with the lower potential energy. The atoms that are participating in an ionic bond will either give or take so that they can form an octet. Okay? They form a crystal lattice, which is the arrangement of that positive-negative alternating structure. And then lattice energy is the energy released when you break it down. Okay? And so I want to take a second to look at the periodic table. We did this before, but we're going to do it again. Okay? If it's a group 1 metal, what's its charge? Or first of all, how many valence electrons is a group 1? Has 1 valence electron. Okay? So is it easier, if they're all trying to get to 8, because 8 is great. Is it easier for it to give away 1 or take 7? Give away 1. So what is it going to what's it going to form? Positive, because we're giving away electrons, which are negative, right? So think of it this way. If I give things away, I'm a more positive person. Or think of it on this level. If I lose weight, I become a more positive person. I mean, I don't know. Usually I do it with size because that's the size of cations and anions. Okay? But you are losing things that are negative. So if you lose your negativity, you become a more positive person, right? If you're gaining negativity, then you're a more negative person. Okay? So group 17 has how many valence electrons? 7. They're trying to get to 8. Is it easier for it to gain 1 or lose 7? So it gains 1, so what's its charge going to be?
-1.
-1. How about group 2?
+2.
It's going to +2 because it's going to lose 2 electrons, become a positive cation. Okay. What about group 16? What are they going to do? They're going to take 2, which would make them a -2. So they would form anions, losing 2 electrons. Okay. If it's in group 16. Just lay it there. Thank you. Okay? Any questions on that? Okay. So I think we're fixing to get that. We do have to do this. Okay. There are 2 types of ions. We call it a monoatomic ion, which mono means what? 1. So that's going to be your elements. And then we have something called polyatomic ions, which are 2 or more items that you're going to add this to. Covalently bonded with a charge. So they're covalently bonded together, but they have a charge, so they will actually act like an ionic compound when they bond. And we'll learn those later on. Now you just have to know what a polyatomic ion is. Later on, you got to learn them. So they're covalently bonded with a charge. Okay. That brings us to metallic bonding. Okay. Metallic bonding, this is occurs between 2 metals. Okay. The results from the attraction are between the metal atoms, and they call it a sea of electrons. Okay, so let me kind of explain that. Basically, I call this like the socialism of bonding. They all share their electrons. Everybody gets their electrons. It's like the socialism of bonding. Okay, so the electrons in a metallic bond don't just belong to one atom. They're like flowing. Okay, which is why metals have the properties that they have. It's why they're good conductors, because those electrons can travel freely throughout the metal, the piece of metal. It's also why they're shiny. It's pretty much why the metals have all the properties that metals have, is because of that sea of electrons. Okay, because they're mobile. Okay, sometimes it's called delocalized electrons, but mostly we call it the sea of electrons because we understand a sea flowing, everybody shares. Okay, so that's metallic bonding. The metallic properties, these are your classic ones: high electrical and thermal conductivity. They have luster, or they're shiny because of the photoelectric effect, and of course they're malleable, ductile. Tensile strength is like how strong a wire would be. All because those electrons are flowing and able to like kind of move around over each other. That's why you can hammer metal out into a thin sheet and it doesn't break apart, because those electrons are able to kind of move around. Okay? Oh, everybody got that? No? Okay.
So the luster is
Oh, we have to add the
the
last
fact that those are moving around.
Yeah, it's the photoelectric effect. So basically what happens is, and we talked about this way in the beginning of the year, when a light of a certain frequency strikes the metal, it takes the electrons and excites them up to the higher orbitals, remember? And then what goes up must come down, and when they drop back down, they release that photon. and that's what we see as light. And it's because of the electrons can move around so freely. Okay? When we talk about compounds with metals, we usually call them alloys. Okay? That's things like brass, sterling silver, bronze. Those are all alloys. Okay? And I think that's left off your notes, so I would add it in. Metal alloys are mixture of elements held together by metallic bonding. So I would add that.
Is this whole slide down on our notes?
No, just right under that, I would just add it in somewhere. Just say metal alloys are mixtures of elements held together by metallic bonding. And we're almost done. So it didn't take as long as I thought it would. Does anybody have any questions so far? Are you good? Anything mind-blowing? Yes.
So, electronegativity increases the more valence electrons you have,
No.
or the less?
No. Remember periodic trends? That is where you have to know your trend of electronegativity. Okay? Yeah. Well, I mean, I can't really say right now. He's taking a test back there. Yeah. After we finish the notes, if you want to come up, I'll tell you privately. Okay. Metallic bond strength, these are the last two definitions we have, varies with nuclear charge. The heat of vaporization is the amount of heat required to vaporize the metal. Okay? It's a measure of the strength of the bond. So basically, the higher the value, the stronger the metal. Which they're going to be really high values. It takes a lot of energy to vaporize a metal. Okay. And then you're fixing to have to fill a chart in because it got left out of your notes. So we're going to pause it and then let you fill in the chart. There we go. So what I would do is turn, oh my goodness, turn to the very back of your notes and fill that chart in.